Okay, if you can find your seats, those late arrivals, please find a seat quickly. We're going to begin the discussion of the third chapter in the text, which is the chapter on fluid dynamics. And now is when we're really going to start working with fluids in motion. Chapter 2 is entirely about statics, or at most rigid body motion, which we saw in the last lecture. But now we're going to be looking at and studying fluids in motion. In fact, today we're going to end up deriving an equation that is extremely useful in fluid mechanics, which is known as Bernoulli's equation, that I am sure you've seen before. It's a very important equation in fluid mechanics, but it is also one of the most abused equations in fluid mechanics, because when you're learning fluid mechanics, you learn about this equation very quickly into the course, like we're going to learn about it today. And then you end up using it, you try to use it for everything. It becomes like a magic formula that you think you can use for just about any problem. And you have to be aware of its limitations. So, a few concepts that are going to show up today. One concept is that we're going to use is the concept of a streamline, or the streamlines in a flow field. Does anybody know what those are? How would you define a streamline in a fluid flow?
Like the direction of the velocity of the fluid?
Yeah, it gives you an idea of the direction of the velocity of the fluid. Could you be precise in a mathematical sense, even before we actually talk about it?
Is it like a unit, a vector in each amount of area?
No, you don't need to invoke unit vectors.
Is it a vector field?
No, they're lines. But what is the characteristic about these lines? He was so far the closest.
Path particle would travel?
Say that again?
Path of fluid particle would travel?
It's not the path, except under a very specific circumstance that we're going to look at. Let me give you the exact definition of streamlines. As I said, these are lines. So you have a flow field. You could draw lines in the flow field. One important characteristic of streamlines is that we think about streamlines in an instantaneous sense. Imagine that you're looking at a flow field and you take a photograph, or you freeze the flow so you can analyze it. So the flow is frozen, or again, take a photograph so time stops. And then you look at the flow field at that time, and then you draw these lines. The condition that these lines must satisfy is that they need to be tangent to the velocity vector at every point in the field. And then, of course, I could let the movie go. So if I stopped it, or if I took a photograph, I can look at the flow field later, and then I will again stop it, look at the streamlines at an instant, and maybe they will be different from the streamlines in the previous view. So one characteristic of a streamline field is that it can change. It can be something now, it will be something different later during the flow. So that's one of the concepts that we're going to look at. Another one is what we know as a steady flow. And for that, let me actually tell you something first. When you think of a flow field, we think of it as a vector field, like somebody said. So we talk about a velocity field. It's a three-dimensional field where I could identify the value of the velocity as a vector at any point in space, which I can denote with a position vector r, and time. So suppose that I have my space, here is x, y, and z, and I have a vector r that points to a specific point in space, and then I also have time. So my velocity field is then a function of space and time. That's a general description of a flow field. What we call a steady flow satisfies a condition. What is that condition? But it has to be a condition on that velocity field for it to be called steady.
It's time independent?
Yeah, that time dependence that we see there disappears. So the general case is that the field is a function of position and time. If it so happens that the velocity field is only a function of position, then we call that a steady flow. What does that mean in practice? That if, let's say we have a flow field in this room that is, say, air moving around because there are vents that are blowing air in and so on. So there is a flow field. If the flow field is steady, then if I look at a point in space and I look at the velocity at that point, it doesn't matter at what time I look at that point. I can look at it now, I can look at it 5 seconds later, 10 seconds later, 15 seconds later. It'll be the same value of velocity at that point. And if I go to another point, somewhere else, same thing will apply. The value there will be the same at any given time. Now, of course, the value of the velocity will be different at different points because, in fact, we see here that the velocity field is still a function of position. But if it doesn't depend on time, then we call it a steady flow. So those are two important concepts, streamlines and steady flow. Now, I told you a moment ago about the streamlines, that if I look at the streamlines in a general flow field now, and I look at them later, they will be different. However, in a steady flow, what happens? If I look at the streamlines now, and I look at them 10 seconds later, what do I find? They are the same, because the flow is steady. If the flow is steady, my streamline field will be also steady, will be the same at any given time. Of course, that's only part of the story. We also have to figure out about forces that are acting on the fluid. So let me show you a couple of very short videos to illustrate some of the points that I'm trying to make. So what is that? A vacuum cleaner. Of course, if you you can hook up the hose on the other side, and it's just like a blower, right? So that's what we have here. This hose is just blowing air out of this top nozzle, and there is a little, maybe a ping pong ball that you can see how it's pretty stable up there. There are no strings. So just the stream of air that is shooting out of that nozzle is holding up that little ping pong ball in place. And even if it gets perturbed, it doesn't fall out of place unless you perturb it a whole lot. So there is something going on here in this flow field. Of course, there are forces acting on that ping pong ball that are holding that ping pong ball in place. But even if you disturb it, there seem to be forces, at least in a certain range of values, that keep the ping pong ball there. So you saw, for example, at some point when I was talking, the person perturbs the ball by tilting the nozzle or even using his hand. Come on, use your hand. There. To push it around a little bit, and it stays, it comes back to its position. There is some sort of stabilizing force that keeps the ball in place. Bernoulli's equation can do a lot in terms of explaining what's going on there, as we will see later on. Let me show you another video. I have a few here. And you can see all of these videos if you go to the, if you have the all access pack and you go to the Wiley website, you have the videos that I'm showing here and many more. I think it's this one. Let's enlarge that. So that's an airfoil. And this experiment is just illustrating the concept of streamlines. So the streamlines here are formed by introducing a die in the flow, which is from left to right. And then as the die progresses, the streamline pattern is formed. And as you can see, there was some time elapsing, but even after some time, those streamlines really don't. The only reason they change at the beginning is because the die is coming into the region near the airfoil. But what would you say this flow is? What type of a flow? It is clearly a steady flow. Because if I look at the streamlines that are already formed, that I can already see there, I don't see them changing in time. So that's an example of a steady flow. Now, if I took that airfoil and I started moving it around, then of course I make that flow unsteady. Those streamlines then would change from time to time if I do anything to introduce a time dependence on the flow. Let's see, I should have one here, this one. Here is an airplane that is, looks like it's landing, and it passes by this tower where there is some smoke. And you can see what it does to the smoke. Have you heard about this? This is why if you travel, if you're on an airplane, the airplane that you're on that is about to take off has to wait. If there is an airplane taking off in front, it has to wait. Same thing for landing. So the air traffic controllers have to keep the airplane spaced by a certain time, precisely to avoid that the plane that is behind gets caught into these so-called trailing vortices that come off the wing of the airplane as it's moving up or down. So if it's taking off or if it's landing, it generates those vortices of the tip of the wings. And obviously, if a plane that comes behind gets caught into that, it can cause some problems. That's another illustration of fluid dynamics. And then I think I had another one here. What is the biker here? Just another illustration of streamlines. This motorcycle in a wind tunnel. The marker is this vapor that you see coming in. And you can see how, obviously, it is used to get an idea of what the streamlines are, where the air is going. And of course, that's why it matters how you design the shape of whatever vehicle it is that is going to be moving through a fluid. The goal is to minimize what? To minimize the drag. So you can see, I don't think there is anything more significant, just different views of the same thing. But they are looking at everything. Of course, here they're looking at exactly what happens behind the head of the biker or behind his back. You can see how there, it's pretty obvious that there are not really any nice streamlines behind. What happens behind an object like that is that there is a wake. And the wake is a problem because the wake increases the drag. So what you want to do when you're designing something in an aerodynamic sense, you want to minimize that wake that forms behind the object because that will increase your drag. Okay, let's go back to the equations. Whoops. So suppose that we want to analyze the forces that are acting on an element. So here is my flow field. There is an x, y, and z coordinates. And I have a fluid element right there, and I want to know what's happening to it. Our starting point typically would be the same equation that we were looking at last time. So if I look at the picture that I want to analyze, suppose that I pick a streamline in a flow field. So whatever the flow, let's say for example we think of that airfoil, and then we have these streamlines, something like that. And I just pick one of them. So I pick one of those streamlines randomly, and I want to look at a short segment of it. So let's say that I take a little segment of that streamline, and there is a fluid element that is passing by that spot in space at any given time. The first assumption that we're going to make as I go along is that the flow will be steady. So let's assume that we're in one of those situations that there is no time variation of the flow field. And remember our equation. So let's write the vector equation that represents Newton's second law, force balance. Negative of the gradient of pressure minus rho g. Let's say that we decide that we are going to orient our flow so that gravity points down on the paper. But that would be the negative z direction. So I'll have my k vector, my unit vector in the z direction pointing up. That's what gives me this minus sign. So minus rho g k, and then rho a. That was Newton's second law for a fluid per unit volume. So, but I'm going to be looking at this little element here. So I'm going to draw it a little larger. So I'm going to draw here. That segment is right here in my exaggerated view. So I have, of course, let's put gravity. So gravity was down this way, right? Acceleration of gravity. I'm going to use, normally you work with x, y, and z for your coordinates. Or if you're working in cylindrical coordinates, you work r, theta, and z. For us, it'll be convenient to use a different set of coordinates that, in fact, are lined up with the direction of the streamline. So I'm going to have a coordinate that is along the streamline. I'm going to call that coordinate S. That, of course, that coordinate turns as the streamline turns. And then there'll be another coordinate that is perpendicular to the streamline. And I'll call that N. So those will be my coordinates when I write the components of this equation. All right, so I made the assumption that the flow is steady. And now I'm going to write this equation in two components. I'm going to write a component along S, and I'm going to write a component along N. All right, so I have, keep that up there. Is that still visible? Yeah. So I will say in the N direction, I'm sorry, let's start with S. In the S direction, what is minus gradient of P in the S direction? Say that again?
Minus G sine theta.
I'm looking at the first term. The gradient of pressure. What is the component of the gradient of pressure in the direction of S? This is why you need to have calculus before you come to this class. The PDS, there you go. So partial P, partial S. So I have minus partial P, partial S. Right? That's from this equation, the first term. Right? And now I need to find the component of gravity in the direction of S. So I'm going to need a little bit more help from here. We need to define an angle. So gravity is pointing down. This is the direction of the normal. So let's call theta the angle that the normal makes with the vertical. So, of course, that's also this angle. So what's the component of gravity in the direction of S? Component of gravity in the direction of S. G sine theta, right? And it's negative. So I keep the negative. Rho G sine theta. Right? And then now the acceleration. Right? The acceleration. I'm assuming that the flow is steady. Right? So when I think of the velocity field, if I go back here, when I'm thinking of the acceleration, it is, of course, the derivative of the velocity in time. Right? And here is a point of confusion, because we said the flow is steady. Does that mean that there is no acceleration? The flow is steady. Is there an acceleration? Huh? No. There could be. Why? Because it's the acceleration of a fluid element that is moving around, right? Yes?
It's changing direction.
Yeah, and that fluid element that is moving around is changing direction. It might be going faster, right? It might be going slow over here and then faster over there. So the fluid element, any of the fluid elements that is moving in this flow field can, of course, accelerate. And this equation is Newton's second law for a fluid element, right? So that's not to confuse with the concept of steadiness. The concept of steadiness is simply that the flow field only depends on position. It doesn't depend on time. However, for a fluid element that is traveling in this flow field, their velocity can certainly change in time in the element's own clock, right, as it goes around. So indeed, there could be an acceleration. Now, I want the components of the acceleration in the direction of S and in the normal direction. The nice thing about picking a streamline as a coordinate, the direction of the coordinate, is that it simplifies the calculation of this acceleration. Because I can write in the direction of the streamline, the component of the acceleration. Suppose that I say that this acceleration has two components. One in the direction of the streamline, maybe call that a unit vector S, and another one in the normal direction with a unit vector N. Right? So those are the components of the acceleration. But if I'm looking now at the component of the acceleration in the direction of S, how can I compute it? As the element moves, say, from here to here, let's say that this distance is ds. When it moves from the beginning of that segment to the end of that segment, what is the acceleration? It'll be whatever the velocity changes from here to here, right, times ds dt, right? The velocity that it, because by the chain rule dv ds dt, I get a dv dt. I get the variation of the velocity of the element as it traverses that segment. What is ds dt? What is ds dt? It's v itself, right? So this is really dv ds times v. And that gives me now the acceleration of the particle as it traverses the segment ds. And so now I can complete my equation here with a, let me write it, it's a product, so I'll just flip it. I'll just write v dv ds, all right? Okay, so same equation, but now we have the component of it in the direction of s. What I want to do next is, so you see how I have a term that is over ds here and another term that is over ds there. I want to do the same thing here by writing the sine of theta. Right? So you can actually see, if you draw a triangle, right, so let me redraw that here. Here is the ds, right? And I'll draw here a dz, because that's the direction of z, right? And the angle theta is perpendicular to this. So this is the angle theta, right? This is also theta. Comparison with this drawing, right? So I can see here that the sine of theta is dz ds, right? The sine of theta. So I can put that into my equation, and now I have minus dp ds minus rho g dz ds equals, and I'm going to do something here. I can rewrite that as, tell me if you agree with me or not, 1/2 d v squared ds, right? Because the derivative of v squared is 2 dv ds. Yes?
In the top, the uppermost equation,
Yes.
there's a rho in front of the A. Why is there no rho in the S direction?
Good question. Why do you think there is no rho in the bottom one? Anybody? What happened to rho? Be brave. Be bold. I forgot it. Right? Rho. Rho. You have to be brave and be bold. If you think there is something wrong, say it. So there is a rho there, of course. I just didn't carry it from the first equation to the bottom. Okay, so I have this equation, which is now a lot more convenient than the previous one because I have ds's everywhere, dd's everywhere, right? Which points to what I might be doing pretty soon here. Huh? Let me put everything on one side of the equation. So I'm going to move everything to one side, and therefore everything will have the same sign. I'm going to put everything with a positive sign. So I'll go ahead and write 1/2 rho dv squared ds plus dp ds plus rho g dz ds, and put everything on one side, therefore I leave a 0 on the other side. I get that. Okay? All right. What should I be doing next? The equation itself gives you the biggest hint. Multiply everything by? Okay, there's a better, more elegant way of saying, you're just kind of giving a step of what I want to do, but what is the whole picture of what I want to do next? Integrate. Integrate across or along what? The streamline, right? So because my S coordinate, remember, is following the streamline. So what I'm going to do is I'm going to take this equation and I'm going to integrate it across the streamline. Of course, that implies multiplying by ds and integrating. So I'm going to leave it for now as an indefinite integral. So I'm just going to say the integral, and I'm just put everything in here. 1/2 rho dv squared ds plus dp ds plus rho g dz ds ds is equal to a constant, right? I'm integrating, so I end up with a constant of integration. Okay, so what is key here is I am integrating along a streamline. That'll be key to remember that. We're integrating along a streamline. So some things to remember about what we've done. We made the assumption that the flow is steady. And now we have made this, we've taken this equation and we have written it along the streamline and we have integrated it. Right? So two conditions so far to retain in our heads. Steady flow along streamline. Okay, okay, let's go ahead and carry out the integration. Let's look at the middle term because that's the easiest one. Right? dp ds times ds integrated, what's that going to give me? P, pressure, right? I'm integrating dp ds over the length, so that gives me the pressure. These two could be harder or difficult unless we make, depending on the assumptions that we make. How do we make it very easy? Gravity is constant. That's a very good assumption. That's not a bad assumption at all. Most problems that you're going to do in your life as engineers, you can assume that gravity is a constant, because the only time it would change really if you're trying to do a calculation that involves a streamline that goes from here to the moon. Right? So then, of course, you might have to deal with the varying gravitational field. But otherwise, G is constant. So that's, we don't even have to make that an assumption. We can just take it as a given that G is constant. But what else?
Density is constant.
The density, right? If I make the assumption that the density is constant, then the other two terms are now also very easy to integrate. Right? Because if that is the case, the 1/2 is constant, the rho is a constant, that comes out. So all I have is the integral of v squared. So first term just becomes 1/2 rho v squared. We already agreed that the second term was p. And the last term is, of course, rho g z, right? And we get this. Which you've seen before, right? In physics. What is this? This is Bernoulli's equation. At least the simplest version of it. The simplest version of Bernoulli's equation. There's a hand up back there.
Yeah, back at the top of the page, can you explain how you went from the v ds to the 1/2 squared ds?
Right here. What is the derivative of v squared? All right, let me put it simpler for you. The function is y equals x squared. What's the derivative of the function? 2x, right? But if I'm taking the derivative with respect to something else, it is 2x times dx something else, right? There you go. So why do I need the half? Because of the 2, right? So it's just a straight calculus, your first calculus, right? Got it? Got to know that. Okay, so any other questions? You can still ask. I'll try not to embarrass you too many times. I don't get embarrassed if you catch that I make a mistake. It's perfectly okay. So if you ask a question and it's the wrong question, same game. So. All right, so what did we say about Bernoulli's equations so far? Because we have to retain those things. In fact, what is that? That will get you embarrassed. So I think I wrote them here so we don't have to repeat everything. Okay, here it is. What are the assumptions that went into it? Steady flow, right? Constant density, right? That was the second one. We integrated along a streamline. We have to keep that in mind when we're writing this equation. We are on a streamline. And that's important in some problems because of that constant. That constant might be different from streamline to streamline. Because we haven't said anything about what happens if I move across the streamline. I did everything following one streamline and I got that constant. If I'm following another streamline, I might get another constant, which is not the same as this constant. So that's important. So you got those three things. There is one more. Steady, along the streamline, constant density. Can anybody think about another restriction? Even though I didn't explicitly say it today. Is there another restriction? The velocity changes with space. That's fine. We allow for that, right? We allow for that variation. You actually have to go back to the very beginning. Where is my first equation? The one that she said I had the rho and then I lost the rho. Oh, here. What is this equation? I've said it many times, so by now you have to know. Newton's second law. Did we leave anything out when we derived that equation? Shear forces. Very good. We left out shear forces. Right? Now, keep in mind that if a fluid is moving in some complicated way, right? Let's say I have this airfoil, and the fluid is going past it. What happens on the surface of the airfoil? Zero velocity. We know that as the no slip condition, right? Zero velocity. But as soon as I move a little higher, there'll be a velocity. So clearly there is shear, right? Because the fluid has zero velocity. Think of the fluid as made up of layers, right? The one on the airfoil is stuck to the airfoil. The next one is moving a little bit. The next one up is moving a little more. So these layers are sliding past each other. And the fluid has something that is important, which is which property? Viscosity, right? That's going to create shear forces, right? So that's a huge restriction because we left it out of this equation. There are no shear forces there. If viscosity does any shearing, or because of the viscosity and maybe a no-slip condition somewhere, there is significant shear, that's not accounted for here. So one easy way to remember the additional restriction is either to think that the fluid has no viscosity. When you apply Bernoulli's equation, you're ignoring viscosity. Or that if it has viscosity, you're somehow ignoring the shear forces. And that's huge. And it's perhaps the most significant cause of error in somebody using Bernoulli's equation in a situation where there is an enormous amount of viscous effects and shear. Right? In fact, I just told you the example by using an airfoil or a surface, no slip. Right? So anytime you're very close to a surface, you have to be careful with the Bernoulli equation. Because by being close to a surface, if the fluid is moving past that surface, there might be significant shear. Right? If you're far away from surfaces, suppose you're analyzing the flow field, as I said earlier, the air that's coming out of the vents is, moving around here somewhere. Well, if I'm looking somewhere here, I'm far from the walls, I'm far from the ceiling, I'm far from you. Maybe there, shear is not a big deal, and I can ignore it. And I can use Bernoulli's equation maybe in most of the space, but not very close to the walls, because then I know I would have to do something else. Other than that, this equation is very powerful. You can use it for a lot of problems. And in fact, even in problems in which there is some shear that is important, some viscous effects that are important, you can still use it as a first approximation to see what's going on. Right? So one thing that, for example, we can understand right away has to do with that video of the ping pong ball above the blower. Right? Because right away we see the following in the equation. If I'm following a streamline, and that the sum of these three things is constant, what happens if one of those terms drops a lot in value? What must happen? Suppose that I take these three terms. One has to do with velocity, one with pressure, one with gravity. Suppose I take the velocity term and I say it drops a lot. From one point to another point, if I'm following a streamline, and from here to here, there's a huge drop in velocity. What else must have happened? Most likely the pressure increased in a necessary amount to compensate. So if you look at the, and of course gravity will play a role because if you move, but typically the last term is perhaps the least important in applications that have to do with mechanical engineering or aerospace engineering. The last term is perhaps the least important because the change in z, in height, might not be very big for your problem. Right? So usually the first two terms are crucial. So if you think of that movie again, where here is the nozzle and here is the ping pong, and I know there is air coming out here, and I can guess that perhaps this air is going to do something like that, right? All right. So that's my scenario. Suppose I'm in perfect equilibrium. It's in the center. It's like pretty much like I have it in this drawing. So it's right center. But now the little ping pong gets moved because the person comes with a hand and pushes it a little bit to the side. So now, perhaps, the scenario is, whoops, I should have moved it to the side. I'll do another one. So suppose that now here is the nozzle, and now the little ball is a little bit to the side here. Right? So of course there is the air still sort of going like that. But if I look over here closer, it might be something like that. All right? So where is the air moving faster? If you go across these lines, or if you look this side versus this side, it'll be obvious that because this is more lined up with the center of the nozzle, that this fluid is going faster, right? The fluid to the left of the ping pong is going faster. The fluid on the right is probably going slower. So what happens to the pressure? It's higher on which side? On the right. Because it goes against the opposite of the velocity. Where the velocity is high, the pressure is low. Where the velocity is low, the pressure is high. So the pressure will be higher here than here. And therefore, it will have the net effect of pushing the ping pong back to the center. And that's why you see that the problem is very much in equilibrium when you see the actual video. Unless you push it way too far, and then of course if you push it way too far, then the weight is much larger than whatever that pressure variation was, and the ball drops. So that's easily explained with the Bernoulli equation, even though we know that very near, right close to the ping pong ball, there has to be some shear. But we just need to look at the velocity field a little bit away from the surface of the ping pong ball, and there we can use the Bernoulli equation. Okay, does anybody have any other questions? Let me tell you, any hands up? There is the other side of the story is, what about the other direction? We did all of this for the direction tangential to the streamline. We also should at least look a little bit about what happens in the other direction. So let's look at the other direction for a second. I'm not going to do it in so much detail, but what happens in the other direction? So we said that, so here is the segment of streamline that I'm looking at. Right? Even though I'm just looking at a little segment and I draw it as a straight line, clearly it has to have curvature because the streamline is turning. Suppose it's turning, except for, I'm looking at a short segment, but obviously there is curvature. And if there is curvature, there must be a radius of curvature. So I can draw a radius of curvature there. And now I'm looking at the same equation, but I want right now the normal component. So let me keep the equation there. And now we're going to go in the normal direction. Well, the component of the gradient in the normal direction, let's say that n, we said s was in this direction, n will be in that direction. Huh? So what is the component of the gradient? Minus dp dn now, right? And the component of gravity, we already did this, so we knew it was sine for s. Obviously, this has to be cosine. So minus rho g cosine theta. It still retains the negative sign because if I have gravity pointing down, it will be in the negative. The component in n will be in the negative n direction. And then the right-hand side. I'm not going to forget the rho this time, so I'm going to put it first. All right, there is a rho. But what about the acceleration term? What is the acceleration in the normal direction? He thinks it's 0. But how is then this bending? Right? This particle is not going in a straight line. Right? Even my segment is a straight line because it's a short ds. That's why I drew the rest of the streamline. If it were 0, this could not turn. So what is it?
I thought the s-axis is changing.
The s-axis? Sure, as the particle moves up, the s will change. But now this is an instant in time. We're just looking at an instant in time. The particle is right here, right now. I know it's going to turn eventually, but at this instant, is there an acceleration in the normal direction, and what is the value of it? V squared over r. That's why you need to take physics before you come here. So, and it's in the positive n direction, right? So V squared over that r. So just like we did before, I'm not going to do it, but just like we did before, we could see what happens, by doing an integration and so on. But let me just give you, in the couple of minutes that I have left, an example. Suppose that I have a flow field. Look at, remember that those vortices that form from the tips of the wings. But also you can think of a tornado. A very simple representation of a tornado, the funnel, right? The motion of the fluid is in circles, right? So if I think of it that way, and I suppose I'm looking from above, and I'm just looking down, I could say that the fluid elements are just going round in circles. As an initial representation of this tornado. So let's say that they're perfect circles of a certain radius r. because I'm looking down the funnel. This is on the plane, which would be like the XY plane. So the Z direction is normal to this, and it plays no role here. So in this particular case, there is no component of gravity here, right? Gravity component is 0, just to get rid of that term. And all we have is then the pressure gradient balancing the velocity. So immediately I know that, that what is happening is that there must be a pressure gradient. Let's just put here dP dN and move the minus sign over there. The fluid is moving in a circle. There must be a pressure gradient that allows for that to happen. And I can, if I know the velocity, if I happen to know the velocity, or if I measure the pressure gradient, I can determine what the velocity is. But where is the pressure then larger? Towards this, in which direction does the pressure increase? The pressure? Which way? For this to go, the force has to be towards the center, right? The force has to be towards the center. So if I plot, for example, a fluid particle here, it has to have a force going that way. Right? And therefore, where is the pressure higher? Towards the inside or towards the outside? Towards the outside. So the pressure has to increase as you move radially out, so that it can actually make the flow turn with a force that points towards the center. So just a little bit about what happens in the normal direction. So I'm going to leave it here, and then when we come back next week, we'll continue using this Bernoulli equation in some specific applications.